Good day and welcome to the Moscow Telecommunication Seminar. Our today's speaker is Danil Shamsimukhametov. Danil received his bachelor and master degrees in applied mathematics and physics from Moscow Institute of Physics and Technology in 2020 and 2022, respectively. Currently, he is a researcher at Wireless Networks Lab of Institute for Information Transmission Problems. His research interests are connected to machine learning applications in wireless systems and traffic classification. And today he will tell us the results of his research devoted to the impact of encrypted ClientHello on traffic classification. Danil, the floor is yours.
Good afternoon, everyone. As Vyacheslav said, my name is Danil, and today I'm going to give a talk named How Encrypted ClientHello Challenges Traffic Classification. It deals with the encrypted traffic classification problem. The talk is based on the article published in IEEE Access Journal and co-authored with my colleagues Anton Kurapov, Mikhail Lubogoshev, and Evgeny Khorov. In my talk, I would like to give a general overview of the encrypted traffic classification problem. I'm going to develop 4 main points. I will start with traffic classification background. Then I would like to give you a small overview of the transport layer security protocol that encrypts most of the modern traffic, and introduce a new encrypted ClientHello amendment to TLS. After that, I will describe state-of-the-art algorithms for encrypted ClientHello traffic classification and introduce the solution proposed in our paper. Lastly, I'll consider experimental results that compare proposed and baseline algorithms. So let me start with an overview of the traffic classification problem. I'll cover 3 main points: traffic classification background, traffic classification use cases, and traffic classification features. First of all, traffic classification is the function performed by networking hardware, for example, controller in the SDN architecture or dedicated device, to infer the type of data contained in every incoming packet and associated with one or few predefined traffic classes. Typical classification object is bidirectional flow of packets having the same 5 tuple. That is a pair of IP addresses, pair of ports, transport layer protocol, for example, TCP or UDP, and traffic classification can be performed online, which is considered in my talk, or offline. The offline classifier typically requires the whole flow. In contrast, the online classifiers aim to identify the class of the flow using the least possible number of initial packets of the flow in real time while the flow is active. Network traffic is heterogeneous. A class may refer to the malware or legitimate, also called benign. The traffic generated by a specific application, for example, Skype, YouTube, WhatsApp, PK, Twitter, and etc. The traffic containing a specific type of data, for example, video, web pages, voice, audio, file transfer, emails, and so on. The online traffic classification is a crucial component of the firewalls in malware detection classification problem. Their purpose is to identify malware traffic as soon as possible and block it, while allowing legitimate users to communicate without any additional delays. Another important problem of traffic classification is early service identification. It corresponds to use cases when mobile operators classify traffic of subscription services that do not count against the client tariff quota. For example, they could count all YouTube flows fully, but UK flows do not count. Is MTS example. Moreover, the online traffic classification is a crucial part of the quality of service and quality of experience provisioning frameworks. In those cases, the traffic type should be identified before any packets with application data are arrived to apply quality of service provisioning tools. Of course, the natural idea is to include the type of traffic in the packet header so that no extra effort is needed to classify the traffic. Actually, this idea is implemented in the IP header with differentiated service called point field, or just diffserv or DSCP. Diffserv is the field in the IP header that should identify the type of data. The sender indicates diffserv that it wants the packet to be treated as. But there is no guarantee this happens, because typically middle boxes do not trust traffic senders and change the diffserv field according to operator's policies in its diffserv domain. The field could change several times on its path. Although diffserv was introduced to provide end-to-end quality of service, it not only fails with it, but also confuses the quality of service provision algorithms. Thus, other approaches are needed. However, encrypted traffic has a stronger traffic class indicator. That is the server name indication extension of the client hello message that starts the secure connection in the TLS protocol. SNI indicates the domain name of the server that the client wants to connect to. Since the hardware server may run several virtual servers with different domain names, and the public key are assigned to the domain name rather than physical devices, the client shall include the server name in its client hello message. SNI-based classification fits well for quality of service traffic classification because most of the servers deploy isolated backend servers to generate traffic with the particular data types. For example, servers with the primary domain Google Video and Netflix Video are likely to carry out video or audio content of YouTube and Netflix respectively, while servers with the primary domain YouTube image deliver YouTube thumbnail images. On the one hand, SNI provides perfect traffic classification. On the other hand, SNI is the weak spot in user privacy because anyone on the line could see your actions. To close the security gap, the TLS working group has developed the encrypted ClientHello amendment to TLS protocol. It hides the most sensitive parts of the ClientHello, including SNI. But there is a question. Does encrypted ClientHello make the server with hidden names indistinguishable? And it's not clear whether encrypted ClientHello prevents traffic classification. Fortunately, useful information for traffic classification isn't limited to these two fields. The peculiarities of particular type of traffic are called features. Typically, the studies distinguish between packet-based and flow-based features. The former involves the content of packet, the header, or payload data. The latter includes the equational and statistical properties of the flow, sizes and inter-arrival times of the packets. Flow-based online traffic classification algorithms have been received much attention in the literature. They extract sequential and statistical information from the packets of the flow and make decisions on them. Their biggest advantage is that they don't rely on encrypted data and work even with fully encrypted traffic. For example, with VPNs, virtual private network. Hence, encrypted ClientHello cannot affect them. However, flow-based classification algorithms require collecting several dozens or even hundreds of packets to achieve high accuracy. Therefore, such algorithms introduce a noticeable classification delay. The majority of state-of-the-art packet-based traffic classification algorithms extract features from the encrypted information of the TLS encrypted flow, the payload data of the initial TLS handshake messages used to start the connection. I move on to the next part of my talk, which is about TLS background. Unencrypted parameters of the TLS handshake that starts TLS connection are main traffic classification features. Encrypted ClientHello will change them dramatically. In the next part of my talk, I'll overview TLS protocol and consider in detail encrypted client hello updates. Transport layer security protocol is the most popular encryption protocol in the modern internet. According to Google and Cisco reports, more than 80% of the global traffic is encrypted with it. The evolution of encrypted traffic has largely changed the traffic pattern. Over the past 5 years, its growth is enormous. The call for security and privacy drives the protocols constantly evolve and release updates. The latest version of the TLS 1.3 protocol, released in 2018, has greatly improved security, and the addition of encrypted client hello expands it even more. TLS operates on the sixth layer in the OSI model. TLS protocol consists of two primary components, the TLS handshake protocol and TLS record protocol, which operates as follows. First, the TLS handshake protocol establishes a secure channel, then endpoints negotiate cryptographic parameters and authenticate via it. Then, the endpoints may exchange information through the established TLS connection with TLS record protocol that provides data integrity. Now let's turn to TLS handshake in more detail. TLS handshake protocol defines three handshake phases: key exchange, server parameters, and authentication. The client starts the key exchange phase with client hello message, which contains the client's TLS parameters. The server responds with the server hello message, which contains the server parameters required to compute the shared secret needed for encryption. Then, in the server parameters phase, the server sends the remaining parameters in an encrypted extension message. Finally, in the authentication phase, the communication parties authenticate via certificates exchange and finish the handshake. Since TLS 1.3, all handshake messages after the key exchange phase are encrypted with handshake traffic secret. Application data is encrypted with another key called the application traffic secret. The client hello and the server hello messages contain several mandatory TLS parameters called fields, such as TLS version, session ID, cipher suits, and center. They present in every TLS hello messages and have the same order across TLS versions due to backward compatibility requirements. The last field contains optional parameters called extensions. They were incorporated in the first TLS version to allow protocol extensibility. Since TLS 1.2, many extensions are used in practice. Since TLS 1.3, some of the extensions have become mandatory, such as SNI and padding. Most extensions may appear in any order, but each extension must appear only once. As for the beginning of 2022, IANA, Organization for Standardization, has registered a list of 59 supported extensions. Also, TLS implementation often contain so-called GRIZ extensions, not registered IANA types, and zero data. According to the TLS protocol, communication parties are required to ignore unknown extensions so that new capabilities may be introduced to the ecosystem while maintaining interoperability. Generate random extension and sustained stability or GRIZ extensions are used to check that the parties conform with this requirement. Every hello message payload begins with fields. They are highlighted in yellow. Some fields have predefined lengths, like TLS versions. Others consist of two subfields, secondary subfield length field value followed by primary data field. Extensions are determined by a unique register type. Each extension in the message is represented with its type, highlighted with purple, length, highlighted with blue, followed by the content, highlighted with green. Thus, the position and the content of every TLS parameter in the message could be easily calculated. Now, I'd like to move on to the main part of the TLS background, which is the encrypted client hello protocol. By default, both fields and extensions are sent unencrypted, raising security issues, as middle boxes can get sensitive information such as SNI. The goal of the encrypted client hello protocol, which amends TLS 1.3, is to protect the TLS parameters that disclose sensitive information about the connection to an on-path attacking. Let me describe its main features based on the latest available specification published in February 2022. But first of all, let me outline some limitations in the client hello protection approaches. Firstly, the client cannot encrypt privacy-sensitive extensions with the handshake traffic secret because it initiates the handshake. Secondly, reworking the handshake so that clients send some parameters after the hello message could cause additional latency due to more round trips over the network. Finally, the client doesn't encrypt anything with its secret key until it trusts the server thereby preventing man-in-the-middle attacks. To conceal real SNI, the developers of Encrypted ClientHello have proposed to introduce so-called client-facing server. In the proposed topology, multiple backend servers with their own domain names store the content and are hidden behind the client-facing server. The client-facing server has a general domain name that doesn't give an external observers any information related to the backend servers. Apart from that, Encrypted ClientHello protocol splits ClientHello into two parts. An encrypted ClientHello outer, which encapsulates only non-sensitive information, and encrypted ClientHello inner. ClientHello inner is sent as a new encrypted ClientHello extension of the ClientHello outer. It has a standard ClientHello structure, including privacy-sensitive extensions such as the SNI and application layer protocol negotiation extension, which is used to negotiate application layer protocol and also sensitive. The inner SNI indicates the domain name of the backend server, that is actual target server. And apart from that, ClientHello inner contains an extension called outer extensions that lists the types of ClientHello outer extensions used by ClientHello inner. The developers of TLS note that even being encrypted, variable length extensions such as SNI can disclose sensitive information through their length. Therefore, they recommend padding extension scheme. Notably, for backward compatibilities, the fields that define the version of the protocol and cipher suites cannot be encrypted. Apart from that, the key share, pre-shared key, and supported version extensions shall be sent unencrypted to allow the client and the server to establish shared secrets. One of the most important for traffic classification, SNI, cannot be simply encrypted for the following reasons. Our server, as I said, run several virtual servers with different domain names. Public keys are assigned to domain names rather than physical devices. Consequently, the server shall be able to define the domain name for which it shall include a certificate in the following message. For that, the client shall include the server name indication in the client hello message. Now, let me describe how encrypted client hello modifies the TLS handshake. The client-facing server publishes the encryption keys and associated metadata for all its backend servers. The client receives the public key of the backend server with the DNS query response and encrypts the client hello inner with it. But note, without DNS over HTTPS, the server domain name can be directly inferred from the DNS query. Then the client sends the client-facing server a message, the client hello inner part of which is distinct for some backend servers. Then following types of handshake are possible. Client-hello inner based handshake. If the client server supports encrypted client-hello and can decrypt the client-hello inner, the server forwards the client-hello inner to authenticated backend server, which will finally result in establishing secure direct connection between the client and the backend server. Client-hello outer based handshake. If the client-hello server supports encrypted client-hello but cannot decrypt the client-hello inner, the client-facing server uses information in the client-hello to establish secure connection with the client and provide him with up-to-date information about the public keys of backend servers. Then the client shall initiate a new retry connection with the provided information, but for security reasons, this information shall not be used beyond the retry connection. Notably, the secure connection between the client and the client-facing server shall not be used for data transmission. There is another possible option if the client-facing server doesn't support SSH, or if the authentication of the client flow out fails. The client must return a failure to the calling application and shall not treat as a signal to disable encrypted client flow. It means that the fields and extensions in the client flow inner shall be valid and suitable to establish secure connection with the client-facing server. Otherwise, the data transmission will be impossible. Finally, in this part, let me summarize the evolution of the TLS handshake protection, which is crucial from the traffic classification point of view. Before TLS 1.3, TLS handshake was unencrypted. SNI, server extensions, certificates was sent in plain text. Then, TLS 1.3 enhanced the protection of TLS handshake data, and only client hello and server hello are unencrypted. But the server extensions not necessary for the shared secret establishment are encrypted. Finally, in encrypted client hello inner additionally finds SNI and application layer protocol integration extension, including their sizes with recommended Python scheme. However, the encryption of the client's other extensions and the particular search implementation depends, and it costs client flow oversizes, but it is possible. Thus, we discussed TLS message structure, TLS parameters that are the main traffic classification features, and the way encrypted client flow changes them. Now, let's move on to the next part of my talk, which is directly about traffic classification algorithms that could be applied to encrypted client flow traffic. Traffic classification is evaluated using two classes of metrics, quality and complexity. Typical traffic classification quality metric are accuracy, error rate, precision, recall, F-score rate. But in this talk, I will pay more attention to an error rate and an average error rate metrics. Their error rate of particular class is a fraction of its misclassified readings. Their average error rate is the mean error rate over all classes. The complexity of traffic classification algorithms is related with such metrics as training time and prediction throughput. Training time is the time that the traffic classification algorithm spends training. Prediction throughput is the number of items that the classifier could predict per time unit, say 1 second or 1 millisecond. In my talk, I can cover two state-of-the-art neural network-based classifiers as the baselines, BGRUA and MATEC. To the best of our knowledge, they have been shown to outperform other parallel-based classifiers. The first classifier uses a combination of two bidirectional recurrent GRU layers, a self-attention layer and a fully connected layer with a softmax activation function that generates probability over all classes. The second classifier passes each input packet to an embedding layer, which extracts low-level features. Then it extracts high-level features with an encoder. The encoder is composed of multi-head attention layers and one-dimensional convolutional neural network feed-forward layer. The dense layer with a softmax activation function generates the probability of various class labels. However, these algorithms have some important limitations. First of all, they are not interpretable black boxes. Thus, we cannot analyze the impact of different TLS parameters on them. Secondly, they consider every TLS parameters, even random, which could lead to additional noises and lower classification quality. Thirdly, the feature extraction procedure of neural network algorithms is extremely time-consuming, while traffic classification algorithms require high prediction throughput. To address these issues, we introduced two novel classification algorithms published last month in the EEE journal. The first algorithm is called recomposed byte-based random forest, or RBRF. It consists of two main parts: payload recomposition that rearranges the payload parameters and assign each a fixed position and a fixed length, and random forest that receives the recomposed bytes of client hello and server hello as a feature vector, and during training process, it builds decision trees, train the random forest, predicts traffic class based on decisions over all trees. The structure or the handshake messages differs for different implementations. Thus, fixed positions of the particular parameters can help the algorithm match the same data from different handshakes and improve the classification quality. Moreover, the predefined byte structure and the architecture of the random forest algorithm make RBRF interpretable. The payload recomposition has two following stages: the payload decomposition, the set of parameters, and the new composition from the parameters. Concerning decomposition, any client hello and server hello message can be decomposed into a list of fields, extension types, lengths, and data. We proposed an algorithm that calculates the position and the sizes of each parameter and associate it with the corresponding list. To define the new composition for client hello and server hello, the proper subset of parameters is selected and defined their fixed length representation and order. Some parameters are discarded because they increase the classification complexity without affecting the quality. The length of parameters of a constant size isn't changed, and the others are aligned to the fixed size. The order of the parameters is shown in figure. The recomposed payload consists of a block of field values highlighted with the yellow, a block with types of the extensions in the order they appear in the message highlighted with purple, a block with the length of selected extensions highlighted with the blue, and the block of the contents of selected extensions highlighted with green. However simplified, the traffic classification scheme can be represented as two consecutive procedures: feature extraction and the class prediction. Features can be extracted using neural networks, as in our baselines, or using an algorithm designed by an expert, such as RBRF. However, the feature extraction procedure is very time-consuming. Unlike the others, our second proposed algorithm is designed to use directly payload bytes aligned to the fixed length as features of random forest. It avoids feature extraction procedures and allows fast prediction throughput. We called it aligned bytes-based random forest, or just ABRF. To compare the performance of various TC traffic classification algorithms, we use the dataset collected by our team. We called it WNL TLS dataset. Dataset contains the download traces of TLS encrypted flows of 4 traffic types: buffered video, buffered audio, uplink, live video streaming, and web. We consider each service for every traffic type as a separate target quality of service class. For the web class, we collect web traces of the download of the 100 most popular web pages according to the HTTP archive site. In addition to them, we treat as web the non-audio and non-video flows generated by audio and video services. We consider the other class as the web class as background in quality of service classification. And overall dataset consists of 12 classes and 3,547 flows. We collect data from the networks in 3 cities: Moscow, Leningrad, and Dolgoprudny. On personal computers, we collect buffered video, buffered audio, and web traffic from Safari, Google Chrome, and Firefox web browsers with Mac OS, Windows, and Ubuntu operating systems. We use Open Broadcast Software Studio on Windows for uplink live video streaming collect. On iOS and Android smartphones, we collect buffered video and audio traffic from the application provided by the corresponding services. The dataset is used to train classification algorithms and to evaluate the performance. For that, we randomly split the dataset into train, validation, and test parts in proportion of 7, 1, and 2 respectively in every round. To run traffic classification, we use a computer, the properties of which are summarized in table with testbed configuration. Note that encrypted ClientHello isn't widely used yet. Consequently, datasets do not contain encrypted ClientHello flows. In our study, we model encryption of the ClientHello messages in 2 ways. The first way refers to encrypted SNI, or ESNI, corresponds to the latest encryption allowed by the encrypted ClientHello specification, where we only encrypt the value of SNI but not its length. To model this option, we extract the ClientHello payload from the first packet of the flow and hide the SNI extension with zeros, as in other related state-of-the-art studies. And the second way, referred to as encrypted ClientHello, or ECH, corresponds to the strongest encryption. We extract the ClientHello payload and remove bytes correspond to all ClientHello extensions registered by IANA, except for the ones that cannot be encrypted. There's a key share, pre-shared key, and supported versions. Also, we update the extensions length, record length, and message length fields of the ClientHello to model the padding scheme. We calculate new values of these fields as previous values minus the sum length of removed extension. Now, let's compare the performance of the proposed classifiers and the 2 baseline classifiers in the scenarios where we used encrypted SNI or encrypted ClientHello encryption. We run the following experiments. First, we'll vary the hyperparameters of the algorithms to study the classification quality complexity trade-off. The first table here shows the hyperparameters of the classifiers that impact their complexity the most and the values that we consider. For the baselines, we underline the default values from the original papers. We do not vary other hyperparameters for both of the baseline classifiers and the developed classifiers because they almost don't impact the performance. And the result plot shows that prediction throughput to the average error rate for all considered classifiers, and both encrypted SNI and encrypted ClientHello encryption scenarios. From the shapes and the relative positions of the curves, we can conclude that the proposed classifiers are the Pareto improvements over the baselines. The choice between the proposed algorithms depends on the service requirements. RBRF provides higher prediction quality, while ABRF shows the best prediction throughput. Each classifier has a plateau in average error rate starting from some key parameter values. The complication of the classifiers almost doesn't impact their quality. We select these starting values to compare classifiers in detail and indicate them in the first table in bold. With the selected hyperparameters, we obtain that RBRF has 65% higher prediction throughput than MATEC baseline classifier, while ABRF predicts twice faster than RBRF. Additionally, we compare the training time of the classifiers and demonstrate that RBRF trains 18 times and ABRF trains 32 times faster than MATEC. Thus, we conclude that both proposed classifiers require significantly shorter training times than the baseline algorithms. This gain is achieved thanks to the absence of the time-consuming procedure of high-level feature extraction and the direct usage of the payload bytes as shallow-level features. The proposed classifiers also show the best per-class error rate. The reason for it is that the baselines learn the structure of the data to be able to find required patterns. This way, they have no filter out the noises caused by random data and changing positions of the informative parameters. Yet, the unseen data introduces other noises, and the informative parameters can change positions differently in the test subset than in the training subset. In contrast, RBRF copes well with different data and encryption scenarios because it trains on well-structured data. As for ABRF, it outperforms baseline classifiers, though it also trains unstructured data. We conclude that the neural network layers that extract high-level features from low-level ones are imperfect. They often convert byte patterns of one class into high-level patterns matching other classes in turn. ABRF directly analyzes bytes as independent features and successfully detects inconsistencies. The obtained results show that the quality of every classifier significantly differs for the ESNI and ECH scenarios. Let me show which TLS parameters contribute the most to this quality gap. We consider 4 cases that differs in the available for classification ClientHello extensions and compare the average error rate obtained with RBRF. Case 1 is equivalent to the ESNI encryption scenarios. In case 2, we fully remove SNI and subtract the SNI length from the message length, record length, and extension length fields correspondingly. However, it turns out that the padding extension also uncovers SNI length because client paid ClientHello to a specific length and other client-side parameters are several independent. In case 3, we remove SNI and padding with the corresponding updates of the message length, record length, and extensions length fields. As a consequence, the RBRF error rate increases by almost 20 times. The last case, case 4, is equivalent to the encrypted ClientHello scenario, the hardest encryption scenario, and the average error rate increases only by 4% over case 3. As the as the main increase in the average error rate occurs when we switch from case 2 to case 3, we can conclude that the unmodified length of SNI has a huge impact on the error rate. Thus, we confirmed that SNI length and even ClientHello padding length contribute the most to the classification quality. However, RBRF still shows a rather low error rate even with the encrypted ClientHello encryption scenario. Thus, we also analyzed which TLS parameters impact it the most with the impurity-based feature importance. The right table shows that both ClientHello and server-hello features contribute to the classification quality. In particular, many ClientHello features which cannot be hidden with encrypted ClientHello, for example, Zephyr suites and supported versions, appear to have high importance. They help distinguish the applications at the client, example, the Vimeo application from Safari application. However, they do not distinguish the flows generated by a single application. For example, video, Vimeo buffered video flows and web flows, both collected from Safari browser. Fortunately, they can be detected by the server-hello features because server settings differ much for various services. The position of the extensions in ClientHello and server-hello messages also have high importance. Besides the presence of grease extensions, additionally diversifies the sequence of the extensions for different applications in both ClientHello and server-hello. Overall, the obtained results show that TLS handshake-based traffic classification could remain possible, even if all services support encrypted ClientHello. To sum up, we have proposed ABRF, a novel traffic classifier that outperforms the best traffic classification known from the literature in speed and accuracy. ABRF avoids time-consuming feature extraction and preprocessing because it inputs raw payload bytes directly to the random forest classifier. We have developed a novel payload recomposition method. The RBRF outperforms ABRF and the best state-of-the-art classifiers in terms of classification quality and outperforms baselines and prediction throughput. We use RBRF to analyze the contribution of different handshake components to the classifier results and conclude that server settings differs much between services and can be sufficient for accurate cost-aware traffic classification. Together with the client parameters, which remain unencrypted in encrypted ClientHello, they form a unique group of features by which target services can be distinguished. That brings me to the end of my talk. Let me go over key points again. I have told you about the traffic classification background. We have looked at TLS protocol and SH amendment. I introduced new classification algorithms and showed that they outperform the best state-of-the-art algorithms. Thank you for your attention. Now I will open the chat and read the questions and answer them. First question. Could you mention the drawbacks of classifiers based on server IP addresses? This approach is widely used by network operators to determine the amount of traffic of various services. Example, to distinguish YouTube, VK, WhatsApp traffic users. Yeah, destination IP address is the huge traffic classification feature, and it's really used, but it is not hidden by encrypted ClientHello. Thus, we didn't consider it in our work, but it is drawback, and it can be used in traffic classification, but it has one problem, that it depends on the location. If I will collect one traffic in Russia and in China, YouTube servers could have different station IPs, and in different locations, classifiers need to be retrained. Slide 30 and 38. What is the proportion of classes in data? Sorry, I didn't include the proportion of classes in at the slide, but they have practically the same proportion. Each class has at least 100 flows, some more, some less, but it doesn't affect the quality. Next question. Following question: can server IP address increase the accuracy of the proposed algorithm? Yeah, of course. The server IP address and the sizes and interval times of the packets can increase the accuracy of the proposed algorithms, and this challenge I want to consider in next work. The goal of this work was to analyze impact of TLS parameters that SSH could close or couldn't close. And of course, it will impact. Slide 41. Could you explain why some traffic types are classified almost perfectly in SSH scenario where the other traffic types have high error rate? Yeah, for example, YouTube live video on Facebook live video was generated by OBS software, and they largely have much more different structure of TLS messages. Some classes have closed TLS structure, thus or closed TLS parameters in their settings. Thus, they if some servers share like parameters, they could be misclassified by classifier. But as we have many TLS parameters, it's not possible. Slide 42. What do you think is the reason why server ciphers are more important than the client? I didn't explain in my talk, but while TLS handshake, ClientHello have a list of extensions and a list of ciphers in the order it prefers, and server choose the cipher that it wants to use more. Thus, the server cipher is the main indicator of the server settings. Thus, it has more impact on the classification quality than a list of cipher suits that client support. Do I answer all questions, or you have additional questions?
Thank you, Danil, for your presentation. I have one question. As I understand from your numerical results, recomposed bytes classifier is the most accurate classifier, and aligned bytes is the fastest classifier.
Yeah.
Am I right?
Yeah.
So can we somehow join these approaches and make the fastest and the most accurate classifier, for example, by increasing speed of the RBRF classifier, for example, by neglecting the least important features?
The speed of ABRF classifier is thanks to the absence of the feature extraction procedure. Thus, if we anyway add this procedure of feature extraction, it will cost the speed of the algorithm. Thus, we couldn't make any additional transformation that will not cost prediction throughput with ABRF. And if we will somehow change RBRF, it will cost and for example, we will take parameters only from the first n bytes of the packet and not consider others. Of course, the feature extraction time will be much less, but it will cost some accuracy. Thus, it is trade-off. In my opinion, it is not possible. Or maybe some new research needs to be done.
Okay, thank you. And one more question from my side is, have you studied the impact of the training dataset on the performance of the baseline and your solution? Because maybe the baseline solutions doesn't have enough data to train, and if we provide them more data, they will be more accurate.
As I understand your question, you think that train part of the data set could be higher, and then classification quality of the baselines will be higher. It is only depend on share of data set, and thus the quality of proposed classifiers will be higher.
Okay, thank you. So I guess that's all for today. Thank you, Danil, for your interesting presentation, and I also want to thank all the listeners for questions and discussion. See you. Goodbye.